Howdy folks, George Babick here, coming to you from the Electronics Cove, and today we have another fun with a Raspberry Pi tutorial coming your way. First, we're going to cover how to connect LEDs to the GPIO pins on the Raspberry Pi, how to determine the resistor size you need for the current limiting resistor. Then we're going to talk about how to use a transistor to drive a higher voltage Blacklight LED, also controlled from the GPIO pins on the Raspberry Pi. And lastly, we're going to go over several techniques, ways to program the GPIO pins to turn the LEDs on and off through software. And when we get to that process, I'll demonstrate an off-the-shelf LED board that you can use if you don't want to have to calculate or figure out what resistor values to use to create your own circuits. So stay tuned, it's going to be a great tutorial. Welcome back, folks. So the first thing we need to do before we determine the resistor value that we're going to use when hooking up an LED to the GPIO pins on the Raspberry Pi is that we need to know the voltage drop across the LED. So the best way to find that is to look at the data sheet. So here's a sample data sheet that shows some typical values that you'll see, in a table in the data sheet that will show you the various properties and attributes of your LED. Pay particular attention to the line that shows the forward voltage drop. This forward voltage drop will give you a typical value that you'll use to determine what kind of voltage that the LED is going to require, which will help you to calculate the current limiting resistor you need to give you the desired current. So let's take a look at the schematic. Notice that we have two pins coming from the 40-pin header of the Raspberry Pi. One of them is going to connect the GPIO 21 pin 40, and the other will connect to ground on pin 39. Then we have the current limiting resistor R1, in which we need to determine its value to give us the right amount of current, and then notice the diode D1, which is our LED, which has a 2-volt drop, which we got from the data sheet. So what we need to do is figure out the resistor values that we need to use to produce these following currents: 2 milliamps, 5 milliamps, or 7 milliamps current within the maximum drive capability. The LED can handle up to 20 milliamps, which is what is stated in the data sheet. However, the Raspberry Pi, depending on how the port pins are programmed, cannot supply that much current. So we're going to limit it to 8 milliamps maximum. Now, if you were to hook up a lot of GPIO pins to a lot of LEDs, you need to be careful because the total amount of current needs to normally be kept under about 50 milliamps. Some Raspberry Pis can supply more than 50 milliamps of current. Some of them may be right around 50 milliamps maximum when you total up all the current for all the pins. So that we can keep this generic for all the different Raspberry Pis, we're just going to do 2 milliamps, 5 milliamps, and 7 milliamps. So let's look at how we go about calculating the resistance value that we need for these three different current levels. So let's figure out the value of R1. First, we have to take the supply voltage from the GPIO pin, which is 3.3 volts. We then need to subtract the 2-volt voltage drop across the LED, that was called the forward voltage, which leaves us with a total of 1.3 volts left. That 1.3 volts will be our voltage drop across the resistor R1, which means we can now use Ohm's law to figure out the value of the resistor using the proper formula. So if we take a look at Ohm's law, it's V over IR. V being voltage, I being current, R being resistance. So you get to three different equations. Voltage is current times resistance. Current is equal to voltage divided by resistance, and resistance is equal to voltage divided by current. So in this case, we know the voltage and we know the current, which means we need to solve for the resistor. So the equation to solve for the resistor is R equals V divided by I. Using the equation R equals V over I, let's see what the resistor values will be for each of the current levels. First, we take 1.3 volts divided by 2 milliamps, which is the same as saying 0.002 amps, is equal to 650 ohms. Then for 5 milliamps through the diode, which makes it a little bit brighter. We're going to take 1.3 volts, divide it by 5 milliamps, again, which is the same as saying 0.005, is then equal to 260 ohms. And then if we want to run 7 milliamps to make the LED even brighter, we take the 1.3 volt drop across the resistor, divide it by 7 milliamps, or 0.007, which is equal to 186 ohms. Now the problem is I don't have a 186 ohm resistor. However, I do have a 180 ohm resistor. So let's use a different equation. Let's use current equals voltage divided by resistance. And let's see if I use 180 ohms, what the current would be through the diode. So in this case, we take 1.3 volts divided by 180 ohms, which is then equal to 7.2 milliamps. So let's take a quick look at the schematic. So notice that R1 is marked as 180 ohms, and it should drop approximately 1.3 volts based on our approximations, and then therefore the current through both the resistor and the diode will be limited to approximately 7.2 milliamps. So let's take a look and see what it looks like. Notice the LED, it's blinking pretty quick. I've got a little piece of code running that turns it on for 200 milliseconds and then turns it off for 200 milliseconds, and that repeats about 100 times. And you can see as we move around how the circuit is wired and should match the diagram. And it connects to GPIO 21, which is pin 40 on the header, and the other pin connects to ground, and that's what's driving the circuit. Keep in mind that if you want to try running the LED at different current levels, you can try the other two resistor values that we calculated for both the 2 milliamps and the 5 milliamps, simply by changing out the 180 ohm resistor with either 260 ohms or the 650 ohms. That'll change the current through the diode. But in this example, I wanted to make it as bright as possible to make it visible, more visible, so I used the 180 ohms and the 7.2 milliamps. So let's take a look at the actual measured current running through our diode. The meter shows 7.35 milliamps, yet when we calculated the value, it's supposed to be 7.2 milliamps. So why does it differ? Why are our approximations off? Well, there's two main factors. First, the resistor has a tolerance. It's a 5% tolerance, which means it could vary in value by 5% high or 5% low. And that will also change from resistor to resistor of the same value. Some will measure high, some will measure low. They're usually not dead on. That's why they have a tolerance rating. Now the diode, we use a 2-volt diode drop, which is the typical value. But the table also showed that it could go up as high as 2.6 volts. So that will vary a little bit as well from diode to diode. So basically we're using a approximation to determine our value. And you can see we're pretty close. We're 7.35 versus 7.2. So we're not really too far off. The other thing that could also affect the final result is that the 3.3 volts we used for the GPIO pin supply voltage can vary as well. It may not be exactly 3.3 volts. It could be a little high or it could be a little low. So that can also affect the overall current through the diode. Next, let's look at a little different circuit. In this case, I have a Blacklight LED that has a forward voltage drop of approximately 3.4 volts. And I'd like to drive this one at 20 milliamps because I want it to be much brighter. The problem is we can't use a GPIO port pin directly because of the higher current and the voltage is higher than the port pin is capable of supplying. So in this case, we're going to use a transistor as a switch. So we're still going to drive the circuit using GPIO 21 on pin 40, except rather than driving the LED directly, it's going to drive the base of our transistor, or basically the base of our switch. And the ground pin on 39 will still be used. It'll be connected to the emitter of the transistor. So we'll need to calculate the value for R2, which gives us enough current to turn the transistor on, but not so much current that it's too high for the GPIO pin. Then we need to follow the same technique as we did before for calculating the value of R1, which is our current limiting resistor, to limit the current through diode D1 to 20 milliamps. Now, since this is a 3.4 volt LED, it's going to have a forward voltage of 3.4 volts. We need a higher level voltage. So we're going to use a plus 5 volt supply, in this case from pin 2 of the 40 pin header. So let's see how we're going to calculate these values for R1 and R2 to light this thing running 20 milliamps through it. First, let's start with the value of R2. Now we know from the data sheet from the 2N3904 that the base to emitter diode voltage drop is going to be between 0.6 and 0.64 volts. We also know that our GPIO pin supplies power of 3.3 volts. So if we take the 3.3 volts, just as we did before in the previous example, we subtract the 0.6 volts across the diode, that leaves 2.7 volts across R2. So now I've selected a 1K, just for simplicity of this example, for R2. So if we want to figure out what current that gives us from the base, driven by the GPIO pin, we take the 2.7 volt drop across R2, we divide it by the value of R2, which is going to be 1K, and that equals 2.7 milliamps. Now the transistor kind of works like an amplifier, so it has a DC gain, what they call HFE in the data sheet. And for this particular transistor, that's between 60 and 300, which means whatever your base current is, because a transistor is a current-controlled device, whatever your base current is, you multiply that by the DC current gain, and then that will tell you what your maximum current is on the collector. So in this case, it's between 60 to 300. So if we take the minimum value, which is 60, we multiply that by our 2.7 milliamps of current we know that flows through the base. That gives us a total maximum, with a gain of only 60, of 162 milliamps on the collector. So we only need 20 milliamps to drive the diode, so that should work fine, and that should keep the transistor turned on well enough that it has a very little voltage drop across it. Okay, so next let's look at R1. So we know that we want to have 20 milliamps of current flowing through our Blacklight LED. And we know the supply voltage is 5 volts and that the voltage drop across the LED is 3.4 volts. So first we need to figure out the voltage across R1. So to do that, you take the 5 volt power, subtract the 3.4 volt diode drop, then that equals total of 1.6 volts across R1. Then we know we want 20 milliamps of current. So then we take 1.6 volts, we divide it by 20 milliamps, which is the same as saying 0.020, and then that will give us a total of 80 ohms. So we want R1 to be an 80 ohm resistor to allow 20 milliamps to flow through our Blacklight LED. One note is that in this design that we're doing and the calculations we're running, we're considering Q1 as if it's a perfect switch. So we're not adding any resistance or voltage drop across Q1 to the equation. It should be nominal enough that it really doesn't affect our output. So let's take a look at what this looks like. I'd like to take just a quick opportunity to say if you're enjoying this video, then we'd ask you please subscribe to our channel and press like below, and we thank you for your support. So let's take a look at how this circuit is wired together. So you can notice in the wiring here that we're coming from GPIO 21, which is right here in the header, GPIO 21, and that is feeding the resistor on the base, which is 1K. Now I didn't have an 80 ohm resistor, so I ended up going with a 82 ohm resistor for the current limiting resistor for the diode. You can see here's our transistor. The emitter is going here, which is the ground. Ground is coming from this pin here in our header, right here. This is the ground, right here. So that's coming into the emitter. Then the base is the center pin, which hooks to our 1K resistor, which is driven by GPIO 21, which is this pin right here, the red pin right here on the header. And then the LED plus 5 volts comes from this wire. It comes over here, and that is 5 volts. This is the way the circuit is wired. So by turning out the lights, you can see just how bright this little ultraviolet LED is. Basically acts as a black light, and it's pretty intense. So for this part of the tutorial, we're going to cover several ways of programming the GPIO pins on the Raspberry Pi. But before I do that, I want to introduce you to a new product. This is the Raspberry Pi LED indicator board, or RPI-LED for short. And this board is really neat because you don't have to figure out your own resistor values or calculate anything to run the LEDs. If you just want to jump right into programming, you can get this RPI-LED board, and it plugs directly into the 40-pin header on the Raspberry Pi. Especially if you're a new programmer and you just want to play, plug this in and write some code, and you're turning LEDs on and off. And not only that, there is a neat little light show that you can download the source code for free. I have a link down below. It also has some details about the board itself and some specifications. But you can get this LED light show, and it looks like this. So let's get down now to the tutorial. So what we're going to do is we're first going to cover using Python. Now, I don't know how many folks know this. The Pi in Raspberry Pi stands for Python interpreter. So it makes sense that we use Python as our first example. So I'm going to go through some examples of how to set and clear some of the port pins on the Raspberry Pi. I'm going to be using the RPI-LED board as a visual aid so you can see the pins turning on and off. Then we're going to cover how to do it in the command line. Now, if you want to learn more about programming the port pins using C code, then I would suggest going to the link below, go to the RPI-LED page, download the free source code, and that's all written in C, and it will show you how to use character device drivers, basically using a built-in device driver in the Linux operating system on the Raspberry Pi. It's not specific to the Raspberry Pi, so it works on many single board computers as long as those single board computers support character device drivers. So it's a way to actually open a driver and talk to the GPIO pins through an actual driver, which is the normal way that most people will access hardware on any system that runs Linux or some type of operating system on it. Okay, so let's get started. So before I start to write the Python program for our demonstration, I want to create a directory. So I'm in my Pi directory, pwd, so I'm in home Pi directory, and I want to create a directory, a subdirectory to work out of. So I'm going to say mkdir python, all lowercase, and then I'm going to change into that directory. And if I do a listing, of course there's nothing there yet. So what I want to do is I want to create the program. So I'm going to type, now I don't have to do sudo or be super user because I'm in the home directory where I don't need permissions to do that. So I'm just going to type in nano, and I'm going to call my program led.py. Hit enter. So the first line that we need to enter in here is a command to the Bash shell that basically tells it what program to run our script. So we wanted to tell it to run Python. So we're going to type in $, exclamation point, user, and this is specific to this particular OS I'm running. Your Python could be in a different spot if you're running a different OS, in which case you'd have to put the path to where your Python is located. Okay, now I need to import the modules that already have some code that I need to use. So and this is case sensitive, so make sure you get the case right. So RPI.GPIO, and I don't want to have to type RPI dot before each GPIO command that I'm going to use. So I'm going to say as GPIO, so I can just say GPIO. Then I want to import time for the delays for blinking the LED. Okay, so first thing I'm going to do is define the pins or the numbers of the pins that I want to use. Now you can make this text anything you want. I'm going to try to make them descriptive for what I'm doing. So let me put a little comment here. Find GPIO pin numbers, and I'm going to say GPIO 21, and that is on the header pin 40, and that's equal to BCM number 21, which of course matches with GPIO 21. Then I'm going to say I'm going to do 3 pins, I think, for this example. So let's do pin 20 right next to 21. GPIO 21, and that's on pin 38 on the header, and of course that's equal to BMI 20. Then the last one, GPIO 16, which is right next to the other 2, and that'll be pin 36. Of course that will be BCM 16 or GPIO 16. Okay, so next I need to set this up to work in BCM mode so that these numbers match the port pins and everything that I'm using. So here, we'll just do, I want to use GPIO, oops, reference numbers. Okay, so to do that, we say GPIO dot set mode to GPIO dot BCM. Okay, that sets our mode. Now let's set up our 3 pins as outputs. So let's type setup GPIO outputs for my 3 pins. Okay, this will be GPIO dot setup, and I need to type my first definition there. I could just put 21 here, but I'm going to put the definition because it helps the code to make more sense, makes it more readable. GPIO 21 underscore pin 40, and that will be GPIO, setting this up as an output. Okay, the next one is the same thing. That'll be GPIO 20 underscore 38. This will also be GPIO.out. And the last one, GPIO 16 on pin 36, and that'll be GPIO.out. Okay, so all 3 pins are now set as outputs. And before we actually do anything with the pins, let me just do a little print statement. And we'll say, let's do a carriage return, and we'll say start of GPIO program. Okay, there we go. Now we want to, I want to flash the LED 20 times. So I repeat 20 times. So to do this, we need to define a variable here. So we're going to say for, let's say loop. For loop in range 20, semicolon, or no, colon. Then we need to hit a tab for our next entry, and this is going to be GPIO.output. Because now we want to set the output. And again, we want to use the same definition. I could put 21 here, but I already defined the pin, which is descriptive, so I'll call it GPIO 21 underscore pin 40. And I'm going to say comma, and I want to say GPIO.high. This will set that pin high. So I need to repeat that for the next 2 pins. And the last one. Okay, so that sets all 3 port pins high, but now I want to keep them on for a little bit of time. So let's just let's take a break. Well, in the code. Take a break. Have a coffee. For 200 milliseconds. Well, that's a very short coffee break. Now we want to set the pins low. So we're going to use the same command as above, GPIO.output, and same pin definitions, GPIO 21, score pin 40, GPIO.low. And we want to repeat this for the following, the next 2 pins as well. And the last pin, GPIO.output, GPIO, and this is last one, 16 underscore pin 36. Okay, so now we set the pins. Wait, whoa, we have to back up. I did not put the time statement. I don't think that the comment is going to cause a delay. We need to actually type in here. We need to put time.sleep 0.2 for 20 milliseconds. Wow, if we would have missed that, we would not have seen any change in the LEDs because it would have been so quick. Okay, so now that we set them high, we took a break for 200 milliseconds. Now we set them low. We don't want to loop back around and set them high again, or we'll never see them go low, so therefore we need another break. Sleep 0.2. There we go, another 200 milliseconds. So that finishes the flashing of our LEDs. Now we need to do some cleanup. So we say GPIO.cleanup. And let's put an exit message. So print, we'll say finished, so carriage return. And we'll say finished flashing. Finish flashing LEDs on the RPI-LED board. Oops. And there we go. So I will leave this up for a few seconds to allow everybody to have a chance to look at it or pause. Hopefully I haven't made any mistakes. We're going to have to come back and edit again, so we'll see. Let's typing this in pretty quickly for the example. So now, since I'm in Nano, I need to save this. I'm going to say Control-O. The file name comes up. I'm going to hit Enter. Okay, just saved it. And I'm going to exit the Nano editor. Okay. So let's do a listing, ls-als. There we go. So we have LED-py. But notice it's grayed out. It is not executable, so we can't run the program. So we need to type in chmod plus x led.py. Now if we do a listing, ls-als, we can see it's executable. So let's give this a try. /led.py. Will it run? Let's see. And it did. Notice it's flashing. Here's the 3 LEDs. They'll flash 20 times, and the program exited, and we just finished. So now we are ready to move on to our next example, and this one will be a little bit shorter. This is just how to quickly set the LEDs, set the GPIO outputs to turn on off the LEDs from the command line. So for that, we're going to use a third-party tool or third-party program called GPIO. So to do that, we will type in, first we have to set the mode of the pins. So we're going to say GPIO-G mode, and I want to use BCM21, which is on pin 40 as we used before, 21. I want to set that as an output. So this sets the mode of the pin just like we did in the Python program. Then I'll do the next pin. I'll light the same 3 pins. So GPIO-G and BCM20, mode, BCM20 as an output. Then GPIO-G mode, and we'll do 16 as an output, just like we did before. Now we're ready to turn the pins on. So first pin, GPIO-G, write to BCM21 and write a 1. This should turn it on. And there we go. First one is on. Now the second pin, GPIO-G, write, and this will be pin BCM20, and set that to a 1. Boom, there we go. And then the last pin, GPIO-G, write, and this will be 16. Same pins we used before, and they are all on. So that if you want to turn them back off, you do the same thing, except you just set it to a 0. So GPIO-G, write 16 for BCM16, and set it to a 0, and it turned it off. So this concludes our Fun with Raspberry Pi tutorial. We hope you enjoyed this video. If you did, please click on subscribe below and like our video. We definitely appreciate your support, and we have a lot more videos and tutorials coming for the Raspberry Pi. And we really hope you enjoy playing with the port pins, the GPIO interface on the Raspberry Pi. So have a great day.